Good morning, everyone, and welcome back to part 2 of session 3. So this is part 2 of novel interventions to improve performance. And in this particular part of our schedule, these are our mini. So these are our mini oral presentations, and they will begin with, they are pre-recorded sessions, and they will have the authors available for Q&A. So if we could start with the first one, Jess, to our team, who is Bianca Probert's presentation called Effects of a Sports Hydration Drink Containing High Amylose Starch on the Hydration Status and Cognitive Performance of Infantry Soldiers. Thank you.
So, I will be presenting on the research we conducted, investigating the effects of a sports hydration drink containing high amylose starch on the hydration status and cognitive performance of infantry soldiers. Infantry soldiers often undertake physically and cognitively demanding missions involving a variety of stresses, such as extreme climatic conditions, for example, high heat and humidity, and radical changes in diet, such as the sole consumption of ration packs, that can lead to poor nutrient intakes. In addition, the use of prophylactic antibiotics, which is common when training or deployed to certain locations, can lead to disturbances in gut function. Such stresses increase the risk of dehydration and the associated decrements in cognitive performance. Meta-analyses have found that fluid losses of greater than or equal to 2% of body mass are associated with impaired physical and cognitive performance. Of interest to reducing the risk of dehydration among infantry soldiers is supplementation with a combination of carbohydrate, electrolytes and high amylose maize starch, which has been found to optimise hydration status in a clinical setting with patients suffering from cholera-induced diarrhoea and in the athletic setting with AFL footballers. The high amylose maize starch is fermented in the large bowel into short-chain fatty acids that improves its absorptive capacity. When hams are combined with the physiological effects of carbohydrate and electrolytes on the small intestine, there is the potential to increase the total absorption volume of the gut. Together, this combination of ingredients increases the body's ability to absorb fluids consumed. So the aim of this study was to determine the efficacy of a two-stage dual-action hydration strategy that combines carbohydrate, electrolytes and hams in a beverage and compare this to the usual hydration practices of infantry soldiers undergoing arduous training in a tropical monsoonal climate. A randomised crossover study was employed with infantry soldiers who were undertaking training in far north Queensland over a period of 11 days. During this period, the average maximum wet bulb globe temperature was recorded as 31 degrees. When receiving the intervention, participants were provided with hydration beverages on 2 occasions. On the first, participants were instructed to drink one 350ml beverage that contained 33 grams of hams on the day before their physical training was planned. On the second, participants were instructed to drink up to 2 350ml beverages containing 16 grams of resistant starch each, immediately after their physical training activity had concluded. The control group was instructed to maintain their normal hydration practices throughout the study period. Assessments included body mass and urine-specific gravity measured before and after activities. Activity monitoring occurred through the use of actigraph watches and researcher observations. Cognitive assessment was conducted using the digit simple substitution test and health questionnaires. Univariate analysis was conducted to determine descriptive statistics and compare study groups, whilst the assessment of the treatment effects on body mass was performed using linear mixed effects models. Our results indicate that the majority of participants, regardless of treatment, were experiencing dehydration of between 1 to 3% fluid loss, as estimated from changes in body mass across the various time points. Overall fluid loss based on body mass changes for the intervention group was found to be less than that of the control. However, after we adjusted for the intervention order and study period, no difference between treatments was observed. However, we did find significantly less sense of thirst reported by the intervention group compared to that of the control. We found that the intervention was safe, acceptable and compatible for use within the field training environment, as indicated by 100% compliance with the intervention and the mild gastrointestinal response reported by the participants. So while the intervention was well tolerated, a significant benefit of the intervention on hydration and cognitive performance was not observed after adjusting for confounders. This is likely due to high intersubject variability related to the inability to standardise conditions in this real-world context. It may also be due to the use of the prophylactic antibiotics and how they may have blunted the fermentation of hams necessary for improved fluid absorption by the large intestine in response to the changes in gut physiology. Whilst the level of dehydration experienced by the study population may not have been large enough to detect a difference between the treatments. We recommend that research continue into the effectiveness of hams and other novel hydration strategies where military members are expected to experience dehydration at levels of approximately 5% in conjunction with suboptimal food and fluid intakes. So that concludes today's presentation and provides us with time for questions. Thank you.
Thank you very much, Bianca. And Bianca's back online again to deal with these questions. And I've got a cheeky one as the chair session again, sorry, but not sorry. With some of the queries that we have in microbiome studies, which is what you highlighted, there could be an issue if they've got prophylaxis antibiotics, is that the actual crossover studies could be actually the problem as it's taking longer for them to wash out. So is that another opportunity for us to, or for you to do the study again, but not do crossover analyses?
I can't say whether we could do the study again. It would be lovely if we could, because there would certainly be improvements that we could make based on, you know, our experience from this study. But absolutely agree, there is that concern that, you know, with crossover studies that, you know, the washout period has not been long enough and therefore has also impacted on the differences that we would have hoped to have seen between the two treatments. We still are looking at the data as well, and I believe that there might be opportunity to explore maybe those effects through some statistical analysis, but I'm not sure on the methodology or on how to actually conduct that analysis myself. But yes, it's definitely one of our concerns with the washout and the crossover study.
Just keeping on time, I know that there's not very much time in a quick rapid presentation, but there are a couple of questions in there if you could pop in and have a look at them for me.
No problem.
And thank you, Bianca. And just a reminder to everyone that as you do put your questions in the Q&A section, please mark out who they are for. So just say hi, Bianca, or hi to whoever has just presented, so that it's easy for them to track those questions and answer them in a timely fashion. Our next presentation is by Sasha Narleen and co, effects of combined cognitive and physical training on cognition in healthy young adults, a systematic review. Thank you.
Hello everyone, my name's Sasha and today I'll be talking about a systematic review we conducted on the cognitive effects of combined cognitive and physical training in healthy young adults. Currently, operational readiness in the ADF is maintained through on-the-job training and physical training of mostly traditional exercises and team sports such as running and soccer. Interestingly, there is some research showing that physical exercise may assist in improving people's cognitive performance, for example, their executive control, memory, and information processing abilities. However, physical training is unlikely to lead to optimal levels of cognitive performance on its own. Further, current training programs do not directly target or measure the improvement of specific cognitive functions. Indeed, enhancing the cognitive preparation and performance of military personnel using effective and affordable training methods has been identified by ADF as priority area for research. Recently, some researchers have suggested that combining physical training with cognitive training may increase cognitive benefits. Combined protocols often look like this, where people are performing some kind of physical exercise while completing cognitive tasks on a screen. A recent meta-analysis that compared combined training to physical-only and cognitive-only training found a small but significant combined training effect on cognitive performance. However, they only examined an older and cognitively impaired population. Therefore, our aim was to systematically review evidence of the effect of combined training on cognitive outcomes in healthy young adults. To do so, we searched for publications studying combined training in the following databases. We searched for studies including combined, cognitive training, and physical training words. We limited our search to publications in English and conducted backward and forward reference searches as well. We excluded publications if participants were not young adults or were physically or cognitively unhealthy, if there was no comparison group, if the researchers did not combine physical and cognitive training or did not measure cognition pre- and post-training, and if the combined group included other training elements besides physical and cognitive training, for example, if participants also completed mindfulness training. Our search found 3,693 publications after duplicates were removed. Title, abstract, and full-text screening excluded 3,684. In total, 9 publications describing 10 studies met our criteria. First, I'm going to explain patterns found across studies before describing studies with positive combined training findings in more detail. In terms of the combined training sequence, 5 studies implemented training simultaneously, where physical and cognitive training occurred at the same time. 2 implemented combined training sequentially, where physical and cognitive training occurred one after the other, and 3 implemented separately, where physical and cognitive training were completed in separate sessions. In terms of the comparison groups, 6 studies included a physical-only group, where participants completed only the same physical training as the combined group. 2 studies included a cognitive-only group, where participants completed only the same cognitive training as the combined group. 5 included another type of active control group, and 6 included a passive control group. Training length varied greatly, from a single 20-minute session to 48 70-minute sessions over 16 weeks. However, I'd like to note that only 1 study was single session, whilst the rest were multiple sessions over 4 to 16 weeks. Across the 10 studies, 10 cognitive functions were measured pre- and post-training. Working memory and cognitive flexibility were measured in 4 studies, visuospatial ability, processing efficiency, and fluid intelligence in 3, attention, memory, motor cognitive coordination, and inhibitory control in 2, and decision-making was measured in 1. Just to note, we scored studies on the Pedro scale to determine their methodological quality, although we did not exclude any studies on the basis of this assessment. We found that none were of excellent or good quality, but 8 were of fair quality and 2 were of poor quality. Out of the 10 studies, 2 reported improved cognitive performance in the combined group compared to all other groups. The first I will describe is Dalloway et al. 2021. In this study, half the participants completed a hand grip task alone, while the other half simultaneously performed the hand grip task and a 2-back and strip working memory tasks. At pre- and post-test, participants also completed a hand grip task at the same time as a 2-back task. Only the combined group improved over time on the 2-back working memory task from 88 to 94%, while the physical-only group remained unchanged. The second study that found a positive effect of combined training was Wang et al. 2019. In that study, participants completed the N-back working memory task after either treadmill exercise or reading academic material. At pre- and post-test, participants also completed the N-back task. Once again, the combined group significantly improved over time on the N-back working memory task, while the physical-only group remained unchanged. So to summarize, 2 studies found cognitive improvements after combined training compared to comparison groups. This could mean that combined training has little to no effect in healthy young adults who may be at their peak on the cognitive abilities measured in these studies. It could also mean that combined training is only effective when protocols comprise of specific tasks and assessments, and perhaps in only certain populations. Interestingly, both studies found medium effects of combined training on working memory, which could be promising. One limitation to this review that we'd like to point out, however, is that the searching, screening, and data extraction were conducted by one person. However, we have now engaged other co-authors to help secondary screen papers and interpret and write up the results. Currently, research into combined cognitive and physical training in young healthy adults is still in its infancy, with all 10 studies we found having been published from 2016 to 2021. Therefore, more high-quality comparable control studies are needed to tease out efficacy, optimal methodology, and feasibility of combined training. Over the next 2 years, with university partners, we are going to run studies comparing combined training versus physical-only training. We will first conduct studies with civilian samples to examine the efficacy and optimal methodology of combined training before examining the feasibility of introducing combined training protocols into the ADF population. We hope to provide an update on these studies at the next DHSS. Thank you.
Thank you to Sasha and her co-authors there. Unfortunately, none of the authors on that list are available for a live Q&A. However, I'm sure there are some great questions there that need to be asked, and we have some of the authors available who can tend to those via the chat function within Hoover. So, keep those questions coming through the chat, and the authors can tend to them later. Moving on to the next presentation is Tom Fay's presentation, which looks at the effect of full motion video from uninhabited aerial systems on maritime picture compilation task performance. Thank you.
Hi, my name is Tom Fay, and I will be presenting on the effect of full motion video from uninhabited aerial systems on maritime picture compilation task performance. The Royal Australian Navy is currently investigating the use of maritime tactical uninhabited aerial system capability for future and current platforms. The term uninhabited aerial system acknowledges that a remotely piloted aircraft is a single aspect of a larger system, including the aircraft, sensor payloads such as an electro-optic camera, a ground control station, and the crew to operator. The introduction of MTUAS capability is expected to provide a number of benefits to Navy operations, including the capability to augment and extend the sensor coverage of the host ship, as well as provide a greater diversity of sensors. There are a number of roles MTUAS could be used for, including forward targeting, communication relays, and force protection. We chose to look at RPA supporting picture compilation, as this is a frequent and critical task, which is the basis from which more tactical tasks can be conducted. There have previously been 2 DSCG studies centred around MTUAS and its possible use in future Navy operations. The first of these studies investigated UAS operator locations, where operators were either co-located with other operators or in a separate room elsewhere on the ship. While the second study had a strong focus on the level of data integration from the UAS sensors into the ops room, as well as UAS payload control and the effects that these had on performance and workload. The current study looked to clarify an aspect of the second study with a particular focus on how the quality of full motion video, in addition to high quality still images, can support operators in a maritime picture compilation task. It also sought to better replicate expected operator tasking during a picture compilation task by incorporating an additional concurrent task. This task required the study participants to answer a series of simple math problems within 5 seconds. The task was selected to represent broader tactical scanning and decision-making tasks and ensure that participants could not simply focus on the UAV video, as it would result in significant detriment to their broader tasking. If the participants failed to respond to the question within the allocated 5 seconds, an alarm would go off to alert them they had missed the question. The study consisted of 26 participants who were recruited from the staff and student pool from DSTG. Each participant was allocated the task of identifying and classifying maritime surface vessels by directing EO sensors on 2 RPAs to collect visual images under 3 conditions. The conditions consisted of either a high-quality still image, a high-quality still image with a low-quality video, or a high-quality still image with a high-quality video. All image collection requests and identifying classification decisions were communicated verbally to an experimental confederate who controlled the EO sensors and entered the decisions into the experimental system. The main focus areas of the study were how the presence of quality of full motion video affected decision time, concurrent task response time, and operator workload. Data was collected through system log files and the NASA TLX questionnaire, which was handed out to participants at the end of each experimental condition in conjunction with a qualitative questionnaire. Participants were informed that their performance in the picture compilation and detection response tasks were equally important and one task was not to be prioritised over the other. Before completing the experimental task, participants underwent a short training session. The training session consisted of a brief provided by the researchers, including the types of vessels that would be present, the RPA, EO capability, and the experimental task. Following the briefing, participants performed 2 practice blocks and were provided with a list of vessel types and example images to assist them in classifying and identifying vessel types, and were encouraged to refer to the booklet during the experiment. The first of the 2 training blocks was a simple task that allowed participants to be exposed to all entities, while the second task introduced the general flight path, mixed video conditions, and the concurrent task. Participants completed 3 experimental conditions with the condition order counterbalanced across participants. Each experimental condition consisted of 24 contacts to be identified and classified within 15 minutes, as well as responding to the concurrent task. Entities were one of 12 possible civilian or military vessels grouped into 3 sizes: small, medium, or large. Each size consisted of 2 civilian ships, 1 allied and 1 non-allied military vessel. Allied military vessels displayed a predominantly blue flag, non-allied military vessels displayed a predominantly red flag, and civilian vessels displayed no flags. Participants were provided with a simple vessel identification criterion. If vessels were a civilian ship, they were identified as neutral, allied ships were identified as friend, and non-allied ships were identified as suspect. As some participants finished the task prior to 15 minutes and others did not, the total number of tracks identified and classified was divided by the total time taken during the scenario. As such, time per track was the quantitative performance metric for the picture compilation task. A repeated measures ANOVA was used to analyse picture compilation task performance and workload for each video condition, while the concurrent task performance was analysed using linear mixed effect models. There were significant differences in track identification time between both the high-quality video and no video condition, as well as between the low-quality video and no video condition. The only significant difference for the concurrent tasks were between the low-quality and high-quality video condition, but the data suggested a possible trend for slower performance in the low-quality video when compared to the still image-only condition. The only significant difference observed in workload was a reduction between the no video and high-quality video condition. The following table highlights some of the themes that came out from the qualitative questionnaire responses in each condition. The general themes that the addition of high-quality video reduced overhead, allowed quicker and easier decision-making through movement around or of the ship, allowing flags or other features to be seen that couldn't be seen in a single image. The other main theme was around the low-quality video and how the high-quality image would usually suffice and the low-quality video would cause operators to be drawn away from the concurrent task in order to make decisions on the picture compilation task. There were some limitations in the current studies that could be explored further or improved in any future studies. These limitations mainly surrounded the participant pool and the tasks that were used for the current study. To support stronger Navy decision-making in this area, future studies should include trained Navy operators and more representative complex tasks. Some minor problems were experienced with the zoom functionality of the still images, but this was thought not to be a major limitation as participants were made aware of this during the training and it was consistent across all conditions. In conclusion, the key takeaway from this study with the inclusion of either low or high quality video reduced decision time in the picture compilation task. However, video quality had a differential effect on current task performance and workload. The inclusion of high-quality video reduced workload and had no significant effect on the concurrent task performance, whereas the inclusion of low-quality video had no significant effect on workload but produced a marginally significant trend to decrease concurrent task performance.
Excellent, thank you, Tom. And I believe Tom is online right now to do the live Q&A. We've got one here, Tom. It says, thanks, Tom. Do you have any views on susceptibility to motion sickness with regards to viewed motion being different to physically experienced motion?
Yeah, I'm not quite sure. Sorry, I just missed the start of that. Are you just able to repeat that question? Sorry.
I can indeed. Do you have any views on susceptibility to motion sickness with regards to viewed motion being different to physically experienced motion?
Yeah, I think it probably plays a little bit, especially in the low quality video, that's probably a little bit jumpy. So with how the frames work in the sort of a video setup. So there's probably some small effects in that, but it certainly wasn't anything we were too focused or looked into as part of the study.
Very good. And one from me, where are you moving to next with these studies? What's the next thing for you?
So yeah, this was sort of a follow on from some previous studies that we were doing with the C129 Navy, like with Navy. I think the next stages would possibly getting trained Navy personnel in and running it again with them, sort of trained operators to get sort of more in depth at how the Navy would use it. We'd probably look to up some of the concurrent tasking as well to be more replicant of what operators may experience as opposed to just some simple math questions off to the side. But yeah, certainly into the Navy space more so than just the DST sort of staff and student pool would be the next steps for this.
And with this secondary tasking that you've got, is it likely that you might adapt that so that it's something that's a bit more real world and something that they'd be interested in tending to ensure that you get that the high level of interaction?
Yeah, I think we'd certainly reach out and get some ideas of what would be better suited, especially in that space, as opposed to what we've done. I think there's probably a bit of thinking and research as to what we'd use for that. But it'd certainly be, yeah, more sort of specific to actual roles than what we have used for this.
Thank you very much for that. We're going to move now to the next presentation. So just keep an eye on there, Tom. There's just had a couple of questions that have popped up late in this feed. So I defer you to go and have a look in there to tend to them. Thanks very much for being available online today.
No worries.
So the next presentation is by Anna White. It's entitled Integrated Multimodal Evaluation of Augmented Reality Information Systems for Active Tasks.
Good afternoon. My talk today is on integrated multimodal evaluation of augmented reality information systems for active tasks. My co-authors are Larissa Cahill, Dom Thulis, Jess O'Reilly, Steve Wiedemann, Ryan Dumman, Steve Cook, Marlon Blanco, and Ed Palmer. In a natural environment, people are able to use sensory information to effectively navigate their environment. They use information about where things are around them to initiate actions and to walk around, and it's really seamless and effortless. A broader question then is, how do people use information displays when interacting with the environment? With the advent of advances in sensing and display technologies, there are new opportunities to present information on head-mounted displays, such as the ones you're seeing here in these images. However, these information displays provide different types of information in ways that may or may not be compatible with the perceptual and cognitive demands of moving through an environment. This project is about understanding how the use of information displays impacts human perception and cognition while moving in the environment, and developing a methodology that can be used to help assess future displays. Our project on information display systems is funded by the Dismounted Combat Program and will come under DST's new Enabled Soldier program. We're investigating human performance, especially perception, cognition, and locomotion biomechanics, in situations analogous to those encountered by warfighters. This project is in two parts. Information displays, as you all know, have benefited from increased computing power and graphics cards. Devices are more powerful and lighter than ever. However, there is still some display latency and/or overhead associated with processing that information. Increased latency, particularly in near-to-eye displays such as augmented reality displays or augmented night vision displays, can impact lots of aspects of performance, for example, user performance, task performance, and it's also been found that the use of these displays can lead to higher rates of forms of simulator sickness. While we know that the human brain can cope with latencies associated with processing information, and that's how we are able to integrate information from all of our senses, which in themselves have different processing latencies, a key question remains, how can latencies associated with information displays be absorbed, and how does this vary with task? And so the aim of this part of the project is to understand how human performance, and by human performance, we're specifically focusing on perception, cognition, and locomotor biomechanics, is impacted by changes in display latency. So in the second part of the project, Project 2, we're looking at the impact of placement of visual information in the visual field on the ability to interact with the environment. So most of what we know about visual processing has been done on humans or model animal systems while they're stationary and often in darkened conditions. So this has told us a lot about the underlying mechanisms, but with new technologies and with increased use of information displays, there are now some really important questions to ask about how sensory processing is affected by movement. So recent results suggest that locomotion can affect sensory processing. In this project, we ask some fundamental questions about how locomotion impacts human perception and cognition. Now, we also know that different parts of the visual field can be more or less important depending on the task being carried out. And of course, visual sensitivity varies across the visual field. Information displays, for example, augmented reality, effectively block part of the visual field. So how does this impact performance? Emerging near-to-eye AR technologies are preserving power and data processing by presenting to just one eye. For example, fused night vision systems with AR overlays present the overlay to one monocle of the binocular systems. So the aim in this part of the project is to fill a gap in the literature that is highly relevant to defence, understanding the impact of presentation of AR information in one eye on human performance during physical movement. So our approach to tackle these exciting problems is to bring together a transdisciplinary team from vision science, sensory neuroscience, computational modelling, human factors, biomechanics, virtual reality, and simulation development. Our approach integrates fine-grained measurement of human perception and cognition with eye movements and locomotion biomechanics data. We're aiming for a holistic view of human performance and real and virtual environments, looking to quantify and understand how the whole performance changes when these information displays are used. The outcomes, apart from building this great collaboration between defence and academia, is to establish experimental paradigms and methodologies for future assessment of human performance with respect to new technologies like information displays used while the human is stationary or moving through the environment. Another outcome will be to provide data to provide an increased understanding of how human performance changes with these scenarios when stationary and when actively exploring the environment. And our studies will cover scenarios where we're actually still in the lab to out in a field trial. So for our defence end users, hopefully these data will allow us to provide recommendations on effective placement of information in the visual field, depending on the task. I just want to say thank you to all the members of our team. So Larissa Cahill, our collaborator from DST with Ryan Dunman, and also Dom Thulis, Steve Wiedemann, Ed Palmer, Steve Cook, and our very capable postdocs and PhD students, Dr. Jessica O'Reilly, Dr. Stuart Miller, Mr. Marlon Blanco, and our new incoming PhD student who's having her application processed as we speak. Thank you very much for your attention, and I'd be happy to answer any questions that you have about the project. Thank you.
Thank you very much for that, Anna. It was a great presentation. We have a few, just little minutes, so just give me a moment. So you're launching into this into the near future, and I'm just wondering when kickoff may be.
So we've actually started on the project, Katie, and we've been working on pilot experiments and hiring people and acquisition of equipment at the moment. So
excellent. And the data collection, when will that be commencing?
very soon, before the end of the year.
We have one question here from Alex Thorpe. Thanks. Is human performance limited to perception, or do you plan to assess performance on task also?
We plan to assess performance on task as well. So we're starting out with exploring very low-level mechanisms of processing that are well characterised and that feed directly into performance on these higher-level tasks. And we'll be using that to inform the development of a high-level task in collaboration with our defence end users and our DST collaborators. And we've had some really helpful workshops around that already.
Excellent. Well, the chat is a little bit quiet. So I welcome other people to engage with this and in the chat function and reach out to Anna as the next part of her work is going to be very exciting. And this will bring our session to a close. We're just going to come back in an hour's time after lunch for our live poster on demand session. And I'm just going to let Jess, our events managing team for Hoover, in the background just to give us some guidance as to what they would look like after lunch. Thanks, Jess. Oh, actually, no, it's not. I'm getting ahead of myself. Sorry about that. My sincerest apologies. We have the next one will be Amanda Douglas. And the presentation is Next Generation Colour Displays and Laser Eye Protection, optimising both performance and safety. Thank you.
Welcome to the effect of in-service laser eye protection on colour perception. I'd like to start by thanking the Office of Naval Research Global and the collaboration with Defence Science and Technology through the Human Performance Research Network for funding this work. And I'd also like to acknowledge my co-investigators, Larry Abel and Maria Gavrilescu. Technology utilised in air, maritime and land vehicle displays is progressing, resulting in a move from monochrome colour displays through to coloured displays. Colour is not only preferred by operators, but it can offer significant advantages with reports of increased efficiency, decreased cognitive load and reduced errors. But how does this interact with laser eye protection? Laser eye protection is commonly required when operating these vehicles, so we really need to know what effect that laser eye protection is going to have on how we view these displays and on displays that we may integrate in the future. Our starting point for this study was, what are we using already? In April, the team travelled up to Oakey in Queensland in between border closures to examine the MRH and Tiger helicopter cockpits for colour usage. Measurements of the spectral content of the different colours displayed was measured, and this was also a really great opportunity to speak with the operators regarding what they consider to be the important and safety critical tasks. We also spoke to the safety officer on base, who identified the laser eye protection currently in service. We popped in a request for this laser eye protection and it arrived in the lab mid-year. So with the laser eye protection in the lab, this led us to our question, what effect is this having on colour vision? Previous standards have asked personnel to just pass the Ishihara plates, and these are a really great screening tool, but they give us no indication of the alterations to colour vision. This is important as individuals have a range of colour perception ability, even within those we consider normal. For this project, though, we've chosen to use relatively new technologies to quantify the effect these laser eye protections have on colour vision by undertaking the task both with and without the protection. The first of these systems on the left here is the one that's in use with the US military, the Colour Diagnosis CCT HD. In this task, the participant indicates in which direction the sea is and the C gets fainter and fainter until the participant is basically guessing. So it's a alternative force choice. This measures exactly how much colour signal our cones need to detect the target against a neutral grey background. The second of these is the system used more broadly in aviation and in the UK. This is the CAD, which was designed and validated by City University. In this test, the participant needs to indicate in which direction the square moves against a neutral grey background of varying brightness. So those speckled grey squares up in the top corner, they're telling me in which direction the coloured square is moving. The coloured square gets fainter and fainter until we can't see it against the background any longer. So it measures exactly how much colour signal we need in a range of different directions. So how far are we moving away from that white point in the centre in each of those different colour directions? How much red, how much blue, etc. So it measures in 16 different directions. So how did our participants go with colour perception when laser eye protection? So here we have some of the really early results from the colour vision testing. I've got the CAD results up first. We have the colour normal observer, which you can see from their results on the left being within the grey normative range for this test. So that very centre there is that white point, and they don't need a lot of colour to be able to pick it up. On the right, we see the same participants' results when looking through the laser eye protection, and here we're seeing a really significant blue-yellow defect, as demonstrated by the wavelengths aligning with that blue-yellow axis on the graph. So thinking about this for displays, we'd need the blue and the yellow to be much brighter than normal in order to be seen. We're also examining the effect of laser eye protection on people with abnormal colour vision. So here we have a deuteranomalous patient, which means they have some difficulty with distinguishing red and green due to an abnormal green cone. This is the most common type of colour deficiency, and we can see this from their CAD results with wavelengths outside those grey circles aligned with the green axis. With a CAD score of 10.19 for red-green, this patient would not have been allowed to fly. Interestingly, though, when we tested their perception through the laser eye protection, we see a similar blue-yellow defect as what we saw with the normal participant, but we actually see improved results with the red-green domain, as demonstrated by the dots being closer to the central circle. So what about the other system? We see similar results. Here we have the results for the colour normal observer, both with and without the laser eye protection, and again you can see the big decrease in blue perception. But what is interesting is the change in the red and the green. As this only tests 3 specific colour directions, the laser eye protection really is shifting the colours presented so they no longer align with our specific cones, and this really skews the results. When we have a look at this for our colour abnormal observer again, we see the deuteranomalous effect of reduced sensitivity to green we're expecting on the left. When we introduce the laser eye protection on the right, we see a big decrease in blue and increases in the red and the green results. This is not our participant magically being able to see colours again, but the effect of the laser eye protection shifting the display. So what are the take-home points for defence? We've demonstrated that laser eye protection significantly alters colour perception. It shifts the display that we're seeing. With the current laser eye protection that we've looked at, this really was causing issues in blue-yellow perception. This will vary for different laser eye protections though, and it will need to be characterised. So we are looking at different options that are currently in use and options that may be used in the future. As this will have a very significant impact on our integration of colour displays, we need to be mindful about the colours presented and how they'll appear through laser eye protection to ensure that we're gaining the desired efficiencies out of using coloured visual displays and not introducing any negatives. We don't want our operators confusing or missing signals. And this may mean that we need to think very carefully about the colours that we use in these displays, depending on the laser eye protection that's required. I'm happy to take any questions.
Thank you, Amanda. The chat is a little bit quiet at the moment, so just give me just a moment. With the laser protection, sorry, just a moment. Where do you envisage that will you be taking this into the near future now that you've finished off this study?
So we will be characterising some of the other LEPs that are available. We've just characterised the ones that came down from Queensland. So we are going to talk through that. I know there's a laser group in South Australia that we'll be talking to and having a look at some of the other pieces that are there. And then it really is around designing and thinking about what colours we should be using in those displays to make sure that we're not seeing any problems with them if we bring them in. I mean, colour displays have a bunch of advantages. That it's an extra channel in which you can kind of segregate out information to help you with your attentional loads. But if you don't factor in the laser eye protection, you might create more problems than you fix, I guess, is kind of the issue there. So it's really making sure that it is fit for what we need it to do.
Indeed. We've got a question here on the chat. It says, "Hi, Amanda. This is from Chris Best. Great presentation. Are there different kinds of LEPs? Do they have a different impact?"
Yes, Chris, there are different kinds of laser eye protection, and depending on which part of the spectrum they cut out, they will have a different impact. And they'll have a different impact depending on the spectrum of what we're trying to see through the display as well.
And this is a follow-up from his question from Chris as well, slightly which is left of field. Could your outcomes have implications for aviation colour vision standards?
Absolutely. So one of the things that we want to look at, and why we were very keen to have a person with a colour vision deficiency in there, is to actually have a look at what levels of colour do we need? Is there an ability for someone who's perhaps got still their 3 cones, but an altered shift in one of the cones? Are we able to perhaps make that much brighter in their display? Could we individually tailor the display for those people to be a more inclusive service? So we are absolutely looking at that as well.
Great. Just keeping an eye on time. I think we've got time for one more. Amanda, that's a great talk. This is from Eugene Naveman. It offers sharp example of equipment integration issues. How do you expect the trade-offs to resolve? Change to protection or to displays, or is it both?
I expect probably to displays rather than to protection. Protection is really kind of set by what the threat is. So depending on what they're likely to encounter, we may have a particular display type that we use. We may make the spectral colours that we're using shift to be particular to that particular protection.
Excellent. Well, I think that's all the questions in there. Just keep an eye on that, Amanda. There may be some more that will come through as people have the opportunities to think about your project. It sounds like it's really exciting. I look forward to seeing where this goes into the future. And probably has a lot of crossover into lots of other domains as well. So with all the interface systems that we use. Thank you. Our next presentation is by Gemma Coleman, using weapon-mounted sensors for combat shooting training. Thank you.
Hi everyone, my name is Gemma and I'm presenting some work that I'm doing for Land Division of DSTG, along with my co-author Mark Viviano, who's from CAT-C in Defence. So the bottom line up front here, this presentation will cover the steps we believe are necessary to design a weapon-mounted sensor for both training and research purposes for defence. I'm going to go through the background to this project, both from the user's point of view as well as the researchers. I'll then go through the proposed methodology that we think needs to occur to make this happen, and then hopefully we can have some questions and receive some feedback from the audience. So my co-author Mark provided the following description of the user requirements in a weapon-based sensor. He says that marksmanship proficiency is critical to combatant lethality in close combat. Defence is seeking efficiencies in small arms training in terms of cost, safety and effectiveness by capturing and analysing data related to motor skills and weapon steadiness in novel settings. In the absence of the objective data required to measure and analyse marksmanship performance in austere environments such as close proximity, variable terrain, and low or no light conditions, Defence trialled a civilian off-the-shelf data capture system, and this is the Mantis X. So it was designed to measure and analyse weapon steadiness in field-based live fire settings. So the Mantis X was attached to the in-service pistol and rifle and utilised to assist coaches in developing near real-time feedback to firers via a smartphone-enabled application. The device was a useful demonstration of concept and indicative of the potential scope of a mobile marksmanship device, although the Mantis X software programs and feedback information are currently incompatible with ADF shooting practices. Additionally, the device proved to be inconsistent with in registering the user movement whilst it was attached to the EF88 in-service rifle. So from the user's point of view, the aim of this collaboration is to identify the requirements for an Australianised device and application for combat shooting training. So it's important to understand how the human and weapons interact with each other in order to support acquisition projects by defining human-related specification, but also to undertake fundamental research projects. Until now, we've utilised subjective feedback from users in regards to design and preferences. As a researcher, we're also constrained to piggybacking off unit training to reduce the administration and safety burden, particularly when attempting novel serials with live weapons. So the WETS isn't a viable option here. So we're talking about combat shooting, where teams of soldiers move through buildings as well as modifying the mass and balance of the weapon. And this can't easily be replicated in this particular simulation. It would be really useful to understand if adding new capabilities and therefore mass to the rifle decreases the quality of movement and by how much. It's also important to us to understand whether users are visually scanning their environment and what the weapon is pointing at while they do that. It's also important to understand safety catch designs and locations, as well as when the user is interacting with it. Lastly, with some of the capabilities that may be introduced in the near future, for example, a weapon-mounted fire control system with a display, it's important to understand how users are interacting with it and if they're maintaining situational awareness of their immediate environment. Motion capture is probably the most useful and easiest way in this type of data collection, but it really is cumbersome and can easily be damaged. So for me as a researcher, I'd like to have an easy to use weapon mounted sensor for combat shooting research, as well as being able to provide a system and methodology to AHQ and CASG to perform acquisition activities with minimal input from DSTG. So the proposed methodology, at the moment, there are three main lines of effort that have been identified to achieve both mine and Mark's aims. So the first line of effort is my PhD, which is looking at stability metrics as well as muscle activity and fatigue in order to differentiate between weapon designs. Line of effort 2, Innovation Central Perth via a Defence Science Centre grant, working on characterising the events associated with combat marksmanship. For example, when the weapon is raised up, when it's down, when the magazine's been changed, and when shots occur, as well as they're also developing an IMU that is soldier-proof with good usability. In line of effort 3, the expressions of interest have been released, and this is in order to do the more scientific aspects of this project. So what we're thinking here is that we need a user needs solicitation, which may be DSTG or Defence-led, to understand what feedback coaches want to see in an app. We'd like to see validation of an off-the-shelf Mantis X system if we end up using that for proving that this type of system can show improvements in performance. We think that we can use the Mantis X system at this point to identify what the mechanisms are for improved performance, and also identifying what good and poor movement patterns are, and then marrying these up with the teaching points from the defence and combat shooting coaches. So later on, if we have shown that this approach is useful, we would also like to develop an app with the right experts, as well as investigate how we can integrate cognitive and physiological sensors to really take the cognitive research to the next level. So the defence relevance statement here is that the testing and evaluation of the human performance aspect of marksmanship will enable defence to optimise equipment design and acquisition, human systems integration and lethality for all personnel. The fielding of a weapon-mounted sensor to identify combat shooting events will inform and validate training systems whilst offering defence efficiencies in cost, time and administration. Additionally, developing a device and understanding the underlying human performance will allow CASG to undertake procurement user trials that would have previously required extensive DSTG involvement, and also our ability to translate that subjective user feedback into useful data. I'm going to leave it there for questions and hopefully some feedback. Thank you.
Thank you very much for that, Gemma. Is Gemma there to take some live Q&A with us right now?
I am.
Excellent. Thank you, Gemma. Got a question here from Phil Temby that says, thanks, Gemma, for an interesting talk. What cognitive sensors are you planning to use and what would they measure for marksmanship benefit?
Yeah, great question, Phil. I don't know at the moment because I'm not a cognitive expert, so I'm hoping that I'm going to find a partner that's going to be able to let me know what kind of cognitive sensors we need. I feel that eye tracking is going to be useful, but again, how are we going to integrate all that out in the field and make it useful for the actual users?
Very good. I'm just going to see what else we have here. With the Mantis, how does this compare to the current wet systems that we have?
That's a good question. I do have my co-author online, but I think that's going to be too hard to try and bring him into this. So the Mantis X is literally a little tiny accelerometer that mounts to the system, so you can use that anywhere. The wet system requires video, it requires a really big simulation system, so it's a building. You have to go to the building, you have to book in, you have to have everything design, all of the software ready and all the simulation, all the simulation happening. Whereas the Mantis X, you can just take it into the spare lot at work at the base and just use it.
Excellent. It sounds like it's a usable in many different functions, which will be less limiting into the future, which will be exciting. Look forward to see where this goes. We've got another question here from Eugene Aveman. Great talk, Gemma. Any plans to add effective markers like fear response to your metrics set?
Again, thanks, Eugene. I'm not an expert in that area, and I would love to have any sort of advice there for what we can do. My expertise is physical ergonomics, so I'm sort of looking at that motor control first, but I really do feel that having that realism will help in training. And again, that's why we're looking for partners and people who can actually advise us on that kind of stuff.
Yeah, sounds like we've got some great things to move into the future, and understanding marksmanship and muscle memory, which are all also brain derived, and how they can assist in your understanding. And sounds like you've got a few people who there you can contact and have a chat with from the cognitive elements, so which is exciting. Thanks very much.
It is very exciting. Thank you.
Gemma, thanks so much for jumping in. We're going to keep moving on to keep to time. And our next presentation is by Salvatore Russo, which is our last one for this session. And that one is entitled Investigating the Benefits and Costs of Target Detection Aids. Thank you.
Hi, I'm David Nicol. I'm writing my PhD thesis on how augmented reality cues can both help and hinder people in military scenarios. This work is funded by HIPAANET Project 9101 and has been conducted in conjunction with our partners at DST and UniSA. I'm standing in for the postdoc who designed these tasks, Dr. Sal Russo, because he is unwell today. Augmented reality visual cues are expected to firstly aid operators by improving search performance and reducing cognitive load in the search for cued objects. And then secondly, redeployment of this now free cognitive capacity should be used to improve search for other non-cued targets. However, classic studies such as Yeh and Wickham's 2001 have found that the benefits obtained from cueing may only exist for the cued targets, and that search performance can reduce for uncued targets. In their study, they investigated visual cueing during aerial search for various targets such as soldiers and tanks. Additionally, one target, a missile, had been designated as a high priority target. A key finding of this study was that when a high priority target, the missile, appeared near a cued target, people experienced attentional tunnelling and missed this prioritised target more often than when that target appeared next to an uncued target. This finding suggests that while visual cues may help improve search performance for cued targets, they might accidentally hinder performance for unexpected high-value targets, therefore reducing overall efficiency. Our study was the first to directly examine this cost-benefit trade-off for simulated augmented reality cues for dismounted soldiers performing Overwatch. We developed this scene in which 4 soldiers are surrounded by people, some of whom will acquire a weapon and thereby threaten the soldiers. Participants are asked to click on all threats, and threats are defined as people carrying a weapon. A small subgroup of people often walk towards a soldier, reveal a knife and attack the soldier. You can see several instances of this occurring in the loop scene. Participants have 2 seconds to click on these threats whenever they occurred. In the condition shown, all knife-carrying individuals were highlighted with a red flashing overlay. This was the valid cue condition. There were 2 other conditions. In the invalid cue condition, a combination of both frequent targets and distractors were cued, thereby making the cues uninformative. In the no cue condition, no characters are cued and participants perform the task unaided. By including both the valid and invalid cue conditions, we were able to compare the effect of the cues when they were both task relevant and task irrelevant. Participants completed 3 trials just as described, but on the 4th trial, a rare target character appeared. This character held an oversized assault rifle and walked across the centre of the screen for approximately 20 seconds. This rare target was never visually cued. You can see him in this scene moving from left to right. The primary measures were the speed and accuracy with the frequent targets, people with the knives, were responded to, and the speed and accuracy with which the rare target was noticed. Secondary to this, eye tracking was taken continually using dynamic areas of interest, and EEG was used to measure neural markers of attention to the flickering cues. To examine the degree to which cueing helps search, we looked at performance for the frequent targets. In the response times, left panel, and accuracy, middle panel, for the frequent targets, we can see that valid cues resulted in faster reaction times and higher accuracy than the other conditions. People also spent more time looking at the frequent targets when they were validly cued, the right panel. Overall, these data show that valid cueing helps performance. Turning to the potential costs of cueing, we were interested in whether cueing might elicit attentional tunnelling that resulted in a high priority uncued target being missed. For the rare target, the character carrying the weapon, people in the no cue condition were significantly more likely to notice the rare target than those in the 2 cueing conditions. This suggests providing cues of any sort resulted in poorer search performance for uncued high priority targets. Further to this, using the steady-state visually evoked potential technique, we were able to quantify the degree to which participants were neurally processing the visual cues. We did this by examining the degree to which the flickering of the cues was mimicked in activity in each participant's occipital cortex while performing the search task. We found that the more a person was dependent on the visual cues, the less likely they were to notice uncued high-priority targets. One interesting and potentially paradoxical finding is shown in the top left panel. We observed that even though people in the valid cue condition were less likely to observe the rare target, the gunman, whenever someone from this group did observe the target, they observed them very quickly and faster than people in the other groups. In coming to understand this effect, we hypothesised that people in the valid queue condition might have been more efficient in their search because they were guided by salient cues, and therefore might have covered more of the visual scene per trial, therefore spending more time looking at the periphery of the scene from which the rare targets entered. To quantify scene coverage, we plotted every fixation during every trial for every person in all conditions, and drew the smallest ellipse that would cover 95% of the fixations. This is a technique borrowed from measuring postural sway. One person's data for one trial is shown on the right alongside the ellipse fitted to that data. We found that the longitudinal axis of these ellipses were longer in the valid queue condition, which can be seen in the lower left figure. Together, this suggests that valid cues afforded more efficient search, which allows them to cover more of the scene. In summary, valid cues attract attention and improve the speed and accuracy with which cued targets are detected. They also increase search efficiency and thus allow people to cover more of the visual scene with their gaze. However, the presence of a salient cue hindered accuracy for uncued high priority targets due to attentional tunnelling towards the cued targets. And we found direct evidence that the degree to which the cues attracted neural processing governed the slowing of detection of high priority events. These hidden costs are important to bear in mind when designing augmented reality visual aids for operational environments. Thanks for your time today, and I look forward to hearing any questions.
Thanks very much, and I apologise, it was actually David who presented that on behalf of the author team there. And we've got David here with us right now to help facilitate that Q&A. So thank you for that, Dave. We appreciate that. We've got a question here from Shane Loft. Thanks for your talk. Do operators doing this task in operational context do so for long periods of time, like a long vigil? Do you think automated cues may impact differentially across time as fatigue or problems sustained attention occurs? Or is there perhaps more benefit?
We suspect it probably will have an impact of some sort, and one of our planned future studies is actually to run a similar study, but bringing fatigue into play to try and see how that might have an impact.
Excellent. We've got one here from Steph Chen. What are your thoughts on using a third-person view in a simulation versus a first-person view?
I must admit I haven't put any thought into that. So the first person, so when we say the third person view, sorry, what are we referring to?
Oh, I just got ahead of myself and lost the question here. I might get you to have a look on the chat, David, because I've seemed to have lost the question in the feed here, which I extremely apologise for. And I'll just move to another question. Many ADF personnel are taught scanning techniques to assist them search for information in complex environments. Have you considered, or are you planning to conduct a study comparing queuing aids with specific scanning methods? And that's from Phil Tendy.
Yeah, we haven't directly thought of that, but it's definitely come up in our conversations about how, you know, we're using undergrad students who don't have any particular scanning techniques, so they're working that out through the training trials. But the expectation is that, you know, with experts trained specifically to do the job, you might get different results.
Excellent. And noting the time, it is 12 o'clock here in Adelaide and 12:30 in Melbourne, which concludes this session in the correct time now. I'm not getting ahead of myself. Thank you so much, David, for jumping on the session today and providing Q&A. And I just have a look at the Q&A. There's a few other ones that would be great to have you answer there on behalf of the team. Thank you.
Will do. Thank you.
Thank you. So noting that I've actually got the right time frame this time round, apologies for that mess up earlier. I was clearly needing to get some fresh air after being in this room in the morning. We will break for an hour and then we'll be meeting back here for a live poster session discussion. And I'm just going to let Jess jump on and give us a little bit more guidance as to what that will look like now.
Hi, thanks, Katie. So as Katie mentioned, we will be coming back at 1:30 for the live poster Q&A. So the Q&A is basically an opportunity for presenters to answer your questions verbally. So we have invited all presenters from the poster sessions to join that session. We still will encourage everybody to ask the questions on Hoover in the Hoover chat and Q&A if possible, and then the presenters will be able to answer those questions verbally. If you haven't already watched the poster presentations, they are available on demand rather than watching them through a live session, and you can find them on the Hoover browser or app in the agenda on Monday. So if you scroll right the way down the agenda to 5 p.m, you'll find the 6 poster sessions, and you can flick through those videos as you like to watch those presentations on demand throughout the week.
Thanks so much, Jess. And the reason why they're there is because the Hoover app doesn't allow us to have them pinned in specific sessions for all of our the block sessions. So that's why they're there. They're not just limited to those timeframes they're allotted to, but you can watch them at any time. So I welcome you to do that. And I will close this session for today. Enjoy your lunch, and we'll see you back here in an hour. Thanks. Bye.